Here you go.
Thank you. Good morning. We went over the first part of this course, basically the background for thermal shock theory. We went over elastic properties, thermal expansion, thermal conductivity, fracture behavior, and then we looked at the theory that's been developed with the different R parameters over the last 40 or 50 years. And we also introduced some other parameters like J1C, the J integral, and rising R curves. So the rest of this course, I picked probably 25 or 30 studies that have been done on a wide variety of refractory compositions. People have tested thermal shock in many different ways and looked at the thermal shock theory in many different ways. So hopefully I'll cover a wide range of what's been done. So I picked out for the first, this lecture, next lecture, 8 papers on alumina silica refractories. And I have 1 paper on silica, which is what we'll do first, and then there's 7 on alumina silica type refractories and what's been done to study their thermal shock behavior. I was thinking that I summarized these papers. If you're interested, I have them in PDF form. If you want them, I can ask Greg to send them to you. Just let me know if you want them, if they're of interest. So the first paper is on a silica refractory. I'm only doing 1 on silica because it's not that common. It's used in coke ovens and glass tank crowns. And it's not even made in this country anymore, I don't think. It's made in China. So this first paper, thermal and mechanical cyclic tests and fracture mechanics parameters as indicators of thermal shock resistance, is a case study on silica refractories. This is pretty recent. It was done in 2019. Okay, well, I'll make sure I get these papers to Greg and have him send them out to you. So you have all these papers if you want to read them thoroughly. So in summary, what they did here is they compared alternate methods for describing thermal shock behavior of silica refractories. And they did basically 3 things here. They took a fracture mechanics approach where they measured the different fracture mechanic parameters. And this is basically monotonic stress strain testing. So that monotonic stress or strain testing is stress or strain testing at a constant rate. They also did some thermal shock testing where they varied the temperature, and they were usually running 5 to 30 or maybe even, I think, 50 cycles in some cases. And they also did cyclic fatigue testing, and they're claiming this simulates the temperature fluctuations. So thermal shock testing produces a thermal stress, but if you put the same sample on a mechanical test machine and cycle it at different strain limits, you can simulate the stresses that develop in thermal shock testing. It's a relatively fast test, and you can do 1,000 or more cycles in a short time. And they're in this paper, they're saying it gives the same kind of results as a thermal shock test. So it's an alternate method of testing for thermal shock without actually doing a thermal shock test. And it's more common lately in the last 10 years. So there were 6 different kinds of materials in this test. 2 conventional silica bricks, which were crystalline. They're commercially available. They contain a calcium oxide mineralizer. And that mineralizer just promotes the conversion of quartz to either tritomite or cristobalite. Basically, the silica in the form of quartz dissolves in the mineralizer, and then tritomite and cristobalite are crystallized out. So tritomite and cristobalite are the desired phases in a silica brick. these bricks were pressed, and there were two of them, silica brick 1 and silica brick 2. Silica brick 1 was fired at 1500 C, and silica brick 2 was fired at 1400 degrees C. And then there were two other commercially available fused silica bricks. These are mostly amorphous. There's some cristobalite and tritonite present. Actually, when I show the chemistry, I think there's 20 or 30% crystalline material present in these amorphous bricks. One of these bricks, fused silica 1, was based on a calcium aluminate cement binder. So it was a cast product and sintered at 1200 degrees C. And fused silica 2 was a mono aluminum phosphate binder. It was pressed and sintered at 1000 degrees C. And then in this experiment, the investigators took the two fused silica bricks and brought them up to 1400 degrees C to crystallize them. So it's not complete crystallization. There's still some amorphous material. So the two fused silica bricks were heat treated to crystallize them, and crystallized fused silica 1 and crystallized fused silica 2 is the notation. And what they tested for mechanical properties, they measured thermal expansion, Young's modulus by dynamic technique, thermal conductivity, and they measured the fracture surface energy. And this is the work of fracture by a wedge splitting technique. And they measured the strength in 3-point bending. So for the thermal shock test, they used bars that were 2.5 by 2.5 by 14.5 centimeters. That's the normal size for a thermal type shock test. And they quenched from 1200 down to 300. And they didn't quench from 1200 down to room temperature. They used this temperature range because they said it is more realistic in an application. It's more severe to take it from 1200 all the way down to room temperature. So they said this is more realistic. So that's their quenching range, maximum 50 cycles. And they monitored the damage as a function of the number of cycles with the dynamic Young's modulus test or the 3-point bend strength. And then the cyclic fatigue was done in 3-point bending at a constant strain amplitude. So the same size bars as in thermal shock, 2.5 by 2.5 by 14.5 centimeter bars. And then the strain amplitude was run between 40 and 100% of the average strain at failure in the monotonic loading to failure. So the strain in the 3-point bend test was used as the maximum. And then in the cyclic fatigue, they were running between 40 and 100% of the maximum strain in a 3-point bend test. So the cyclic fatigue was done at different strains. So these are the properties of these silica bricks. SB1 and SB2 are the crystalline materials. FS1 and FS2 are the fused silica materials. So the crystalline materials were about 96% silica. And then the mineralizer CaO was about 2.5%. And this one, FS1, is about 97% SiO2. And then you see there's alumina and calcia less than 3%. And that comes from the calcium aluminate cement binder. And then FS2 is about 98% silica. And then the mono aluminum phosphate, you see the aluminum oxide and the phosphorus oxide over here, 0.5 and 0.4. So those are the materials. Their densities were similar. The true densities weren't that different. But the apparent porosity in this one was lower. There's a denser material. And then the thermal expansion was measured from room temperature to 1000 degrees C. So 1.2%, 1.3% are typical for a crystalline silica material. And then the fused silica materials, 0.3 and 0.1. So they're fused silica, they're real low expansion. And then the asterisk over here is after the heat treatment at 1400 degrees C. So when you crystallize the material, you're up to 1.3 and 1.4, similar to these. And the dynamic Young's modulus, this is in gigapascals. Both of the crystalline silica bricks start out around 11 or 12. And then when you go through the phase transitions for cristobalite and tridymite, the modulus becomes a little more than double. The fused silica here has the low modulus, but then as you go to higher temperatures, it also goes through, there's some crystalline material present. It also goes through the phase transitions and increases. This one starts out really high because of the low porosity, and then there's some, again, some crystalline material present, so it increases at the higher temperature. And then the ones with the asterisk have been heat treated. So once they're heat treated and you start forming tridymite and cristobalite, you form microcracks. So these values are pretty low. And that's the idea here, is to heat treat these two materials, the fused silicon materials, create microcracks and see their effect on thermal shock behavior. And then going through the transition again, they increase. They also measure the thermal conductivity and the heat capacity. These are just typical values for those two properties. So the phases present, SB1 and SB2, the crystalline materials, 20 to 30% cristobalite, 60 to maybe close to 80% tridymite, a little bit, a fraction of a percent residual quartz. And then the mineralizer, the lime, the CaO, creates wollastonite. That's a calcium silicate. So there's a couple percent wollastonite due to the mineralizer. And then FS1, as received, has 30% crystalline cristobalite, and it's about 60% amorphous. And the calcium aluminate cement reacts with the silica and forms an undesirable phase anorthite, which is a low melting calcium aluminosilicate. So as they increase these times at 1400, they did 24 hours, 48, and 100. The cristobalite content goes up to about 80%. The amorphous content drops to about 15%. And FS2 had about 11% cristobalite and a little tridymite present. So it was close to 80% amorphous. And this was the one made with the monoaluminum phosphate. So heat treatment at 48 and 100 hours, the cristobalite content increased to almost 80%, and tridymite almost 10%, and the amorphous content dropped to about 14%. So looking at the microstructures here, the marker's a 0.5 millimeter. This is SB1, the crystalline refractory. It's got a pretty fine upper aggregate size here. They're about a 0.5 millimeter. So you can see the fine aggregates and then the matrix regions in between. And they noted that there were no microcracks here, and you wouldn't expect microcracks because it's all the same material, regardless whether it's a coarser particle or the matrix. There's no thermal expansion mismatch between the coarser grains and the finer matrix. And this is the second crystalline silica brick, SB2. You can see this one has larger grains on the order of maybe a couple millimeters. And then the matrix and then the finer grains. So again, no microcracks were really seen because there's no thermal expansion mismatch between the matrix and the coarser grains. And then this area was looked at a little higher magnification. So this bar is now 0.15 millimeters. So here's a coarser aggregate. Here's another coarser one, and then here's the matrix regions. And this lighter colored material is just the epoxy resin when they made the polish section. So again, they didn't see any microcracks, and you wouldn't expect any because the matrix and the coarser grains have the same thermal expansion. So this is a crystallized fused silicon materials, CFS1. These lighter regions, they're marked A. There's some over here. They're residual amorphous material. The rest of the material is crystallized, and this one happened to be in the form of cristobalite. So it's pretty fine crystalline structure with some residual amorphous materials. So now they start seeing microcracks because there's a significant thermal expansion mismatch between the amorphous materials and the matrix or the crystallized material. You can see the microcracks forming here. So the crystallized material upon cooling is contracting a lot more than these amorphous particles. So they're being put in compression and they're forming microcracks. And this is the other amorphous material, CFS2. There's some areas here and over here. You can see them, quite a few areas that are still amorphous. And then if you look at higher magnification, here's an amorphous particle, and you can see cracks, microcracks forming around those particles. So now there's a thermal expansion mismatch, and the material is microcracked. So the investigators here deliberately crystallized the amorphous silica bricks to create a microcrack structure. So thermal expansion was measured as a function of temperature. And this goes from 0 to 1.4% and 0 to about 1400 C. The solid line, and then this line of the small squares are FS1. The solid line is FS2. So these are the amorphous materials. So their expansion is quite low. And then the triangles is the SB1, a crystalline silica brick. And then the gray colored squares are the crystallized fused silica brick, CFS1. So once it's crystallized, it has the typical behavior for a crystalline silica brick, and these rapid increases here in thermal expansion are due to the phase transformations of cristobalite and tridymite. So these authors were going to calculate the different R parameters like RST and R4 prime, but because of this type of behavior, nonlinear thermal expansion behavior, they decided not to calculate the parameters because they didn't know where to take the thermal expansion. Basically, the same thing happened for Young's modulus versus temperature. They didn't calculate the R parameters because of the nonlinear behavior in Young's modulus. So these are the same four materials as over here. SB1 is the crystalline material, the triangles. that's this curve here, heating and then cooling. Um, you can see the effect of the phase transformations and then the increase in modulus as a result of the phase transformations. FS1 is the open squares. Actually, that's heating and then that's cooling. There's a little crystalline material present, so you see a phase transition, and you take it up to this temperature, you crystallize it a little more, so you have a little more of abrupt change here. And then the crystallized fused silica CFS1 is the gray colored squares. So that's going through the phase transitions again. And then the last one here, the solid line, the fused silica 2, it starts out a little bit of increase due to the phase transitions, but it crystallizes quite a bit. And upon cool down, you see this bigger change because of the higher crystalline content. So because of this wide range in Young's modulus, it goes from 10 to 40 GPa. And by the way, this one is much higher because it has the lowest porosity. And they elected not to calculate our parameters because this is very much nonlinear. So a low displacement curve for the silica bricks looks something like this. These are typical 20 degrees, 800 degrees, and 1100 degrees C. So this one is 20 degrees, 800 degrees, and then 1000 degrees. So they're pretty linear, and then they're somewhat stable during fracture. And the higher the temperature, the lower the load. So that's for a crystalline silica brick. The same plot, load displacement curve. We have the fused silica brick number 2 at this 3 temperatures, 20, 800, and 1100. So they're right here. So this is actually this is 20, this is 800, and then this is 1000. So they're also fairly brittle, pretty linear to failure, and then somewhat of a gradual decrease. But then the 3 that are shown here at 20, 800, and 1100 degrees C were the same material but crystallized. So it's much weaker, it's highly microcracked, but the failure is extremely gradual. It takes the strain here, the displacement is very large compared to these. So it is a less brittle material. It's highly microcracked. And this kind of stress strain curve is going to give much improved thermal shock resistance compared to this one. So this is MOR versus strain at failure. So SB1 at 20 and 1000 degrees C are these squares, this one and this one. And SB2 are the circles at 20 and 1000, this one and this one. So they're up here, they're stronger, but the strain to failure is lower. And then FS1 at the 2 temperatures, 20 and 1000, are also up here. They're also brittle. They're a little weaker, but the strain to failure is pretty small. But then the 2 crystallized materials, CFS1 and 2 at 20 and 1000 degrees C, are over here. So lower strength, higher strain to failure. These are again microcracks, so they should give better thermal shock behavior. So these strains for these different material were the strain limits used for the cyclic fatigue. So you can't run a cyclic fatigue at a higher strain than the failure strain. So they were running at about 40 to less than 100% of these strains that are shown here for these different materials. So this is the maximum stress in the wedge splitting experiment, and they called it SIGNT in megapascals from 0 to 12. So the maximum stress in the wedge splitting test versus the work of fracture, the fracture surface energy that was measured. And the crystalline material SB2 at the three temperatures, 20, 800, and 1,000, are these circles. They're over here. The fused silica are the squares at 20, 800, and 1,000. The squares are up here, but then the triangles are down here. That's the crystalline fused silica material at the three temperatures, 20, 800, and 1,100. So they took a much lower load in the wedge splitting test, but they also have the higher work of fracture. So they also took the ratio here. GF is the fracture surface energy in the wedge splitting experiment. So it's this fracture surface energy divided by the maximum stress in the wedge splitting experiment. So they're just taking this value, dividing it by this value, and they're putting these lines of constant ratio from about 5 to 60 on this graph. So what they're looking at here is a brittleness ratio. So the higher the ratio of fracture energy to this maximum stress in the wedge splitting experiment equals lower brittleness and higher thermal shock resistance. So these are going to have higher strains to failure, higher work of fractures. So the higher this number in this area here, like 30 to 60, the lower the brittleness, the higher the thermal shock resistance. So one of the things they've done here is measure thermal shock resistance in terms of this brittleness number. So this is the brittleness, the work of fracture surface energy divided by the maximum stress in the wedge splitting experiment, brittleness versus displacement at failure. So the triangles here are the crystalline fused silica at these three temperatures again, 20, 800, and 1,100. They're up here, and then they're all in this upper area. And then the circles and the squares are down here. The circles are the crystalline silica brick, and the squares are the fused silica brick. So their brittleness numbers are low. That means they're very brittle, very little displacement at failure. When you get up to the higher brittleness numbers, that means they have low, they're not brittle, they're more ductile. It seems like the higher brittleness number should be more brittle, but the way it's calculated, the higher the brittleness number, the lower the brittleness. So the higher ratio of fracture energy to this stress, maximum stress in the wedge splitting experiment, the higher the strain to failure, and the better the thermal shock resistance. So here's a plot of residual MOR versus residual Young's modulus. So there should be a general relationship where they follow a curve here. This is residual MOR for a crystallized fused silica brick. It's 71%. And then this is residual MOR for a silica brick that's crystalline. It's only 37%. So here are the three samples that are shown here, the open, triangle, circle, and square. And then those are for the crystalline fused silica. And then this is for the crystalline silica bricks. The solid, triangle, square, circle, or diamond. So when they went through 50 thermal shock cycles, they drew the crack pattern that they saw. So you can see the crystalline bricks have a lot more cracks present, and they're much more severe. So the single line represents a thermal shock crack that was observed. The solid line is where the fracture took place during the MOR test. And then the double line is where the MOR took place if it wasn't at a crack. If it's a solid line, it was at a thermal shock crack, and it was also where the material fractured during the MOR test. So there was a crack present here, and that's where fracture took place. These have hardly any cracks visible, and that's where the MOR and three-point bending, where the failure took place. You can see it's pretty much in the center. And then the failure here was along an existing thermal shock crack. These two are near the center. These are severe cracks way off center, where the very low bending moment. So these were severe cracks. So there's a general relationship with residual MOR. The higher the residual MOR, the higher the residual Young's modulus. And in this case here, the crystalline bricks are much more severely damaged than the fused silica bricks that were crystallized. So they did some optical photographs of the surfaces of these materials. So this is the field of view for a crystalline silica brick after 50 thermal cycles. You can see the crack here, see another crack here. These cracks are very straight. Ideally, for a thermal shock material, you want a very tortuous fracture path to dissipate as much energy as possible. You want to see a crack bridging. You want to see crack branching, micro cracks forming. And this crack is straight. This is a coarse grain. You can see the coarse grains in the lighter colors. The crack goes right through the coarse grain. It doesn't deflect around it. That's the worst possible situation for making a thermal shock resistant material. So cracks were straight and they were transgranular right through the grains without deflecting. And this is after 50 thermal cycles for a crystallized fused silica brick. I find it hard to see the cracks here in these pictures, but the cracks are following these tortuous paths. You can see the coarser grains. They're actually going around them along the matrix coarse grain interfaces. So this is a more tortuous fracture path, more desirable for a thermal shock material, thermal shock resistant material. So the last few slides here on this silica material. This is damage versus number of cycles. So the damage, the way they calculate damage D, D is the damage. It's 1 minus EI over E0. EI is the modulus measurement after the ith thermal cycle, and E0 is the initial modulus. So as you increase the number of cycles, E becomes lower, EI becomes a lower number. You're subtracting a lower number from 1, the damage goes up. So the higher this value for the damage, the lower the elastic modulus. So this was for the crystalline silica brick SB1. There was 4 samples here. And you can see the cycles, 50 cycles in thermal shock damage. So the damage goes up and then tends to level off. And then the solid lines were the mechanical cycles, and all of this testing is at 1,000 degrees C. So the authors are saying, well, look, here's the mechanical cycling. We look at 50 cycles. It's pretty similar. Here's another one up to 50 cycles, and here's another one. This one had actually failure after maybe 25 cycles. But in this area where there's less than 50 cycles, it looks like there's a lot of variability in these materials, but it looks like you can use mechanical cycling to simulate thermal shock behavior. So this goes from 0 to 1. This is for the crystalline fused silica, same type of plot. This only goes from 0 to 0.4. So the damage is much less. So these were 3 different samples of crystalline or crystallized fused silica. You can see the damage pattern as you increase the number of cycles. And then the solid lines, again, are the mechanical fatigue testing. And this one didn't last very long, but these two are somewhat similar. And the damage, again, is calculated by 1 minus EI over E0. So D is damage, EI is the modulus after the ith cycle, and E0 is the initial modulus. And these are all done at 1,000 degrees C. So if we look at this type of plot, this is cycles to failure versus strain. And then this is stress versus strain divided by strain to failure. So the gray curves are the monotonic loading, the 3-point bending. So they're pretty linear to failure. This is the failure stress, and this is the strain. And then there's an abrupt failure. And then this solid bar is the monotonic strain to failure. So about 0.2% is the strain to failure for these materials. And then in the cyclic test, cycles to failure from 1 to 10,000, and then the resulting strain divided by the strain to failure. So this is going from maybe 45 to 136%. So this is the strain to failure, this number here, and then this is the percent that was used in the cyclic test. So this was about 40, maybe this was 50 percent strain over this total strain to failure. So these were lower loads, lower strains during the cyclic test. And then as we go up in this direction, they were cycling at higher strains. So when you reach a higher strain, the solid squares indicate they failed after this many cycles. And these didn't even fail at the lower strains after many cycles, maybe somewhere between 1,000 and 10,000. And then they did the same thing for SB2. You can see the stress strain curves are pretty linear to failure. This was the strains observed on that type of stress strain curve, and then the number of cycles, and then the percent strain that was used in the test. So the open squares did not fail, and as they increased the strain percentage, these solid squares failed after so many cycles. And then the crystallized fused silica samples. If you look at the stress strain curve here, you can see it deviated quite a bit from nonlinear. It was not an abrupt failure. You have this gradual failure. This is a much better stress strain profile for a thermal shock resistant material. And then the cycles to failure. This is they calculated the maximum strains off of the maximum in these curves here. And that's your strain to failure. And then the percentage that was used in the cyclic test go from maybe 39 to 118. So the opens squares did not fail at the lower strain percentages, but as you increase the strain percentages, this one was actually higher than 100%. They failed. This one failed after a few cycles. And they did the same thing for CFS2, the crystallized fused silica brick. So the stress strain curve exhibits nonlinear behavior, gradual failure. Here's your maximum strains in this region here. Then the number of cycles versus the percent strain are for the different squares here. These did not fail. A higher percentage showed a failure. So if you look at the stress strain curve, you see the failures are taking place under these curves here, and the non-failure is above these curves. So that they summarize this behavior on this graph here: stress versus strain. SB1 and SB2 are the crystalline silica bricks. CFS1 is a crystallized fused silica brick. So these cycle many times, very little damage, but when failure takes place, it's pretty catastrophic, and failure takes place at a pretty low strain, less than 0.2%. But the crystallized material that's highly microcracked shows this kind of behavior as you cycle it. At the beginning here, you're forming more microcracks, and existing microcracks are growing. And then as you increase the number of cycles and the strain, you start having frictional and bridging effects in the crack weight in this region here. And finally, all these cracks start to link up, and you finally have a gradual failure, but the strain is pretty high. So this is a profile in the cyclic testing that would give a material with good thermal shock resistance. And this is a profile that would give poor thermal shock resistance. So there's a lot was presented here. To summarize it, the microstructure, the silica bricks, the crystalline silica bricks, they were tested as very brittle, few microcracks, minimal thermal expansion mismatch between the coarse grains and the matrix. A few silica bricks were also designated as brittle. Again, few microcracks due to minimal thermal expansion mismatch between the coarse grains and the matrix. But because of the lower thermal expansion, that enhanced their thermal shock resistance. The crystallized fused silica bricks were more ductile. They were very low in the brittleness rating. They had microcracks due to thermal expansion mismatch between amorphous regions and the crystallized grains in the matrix. So strong coarse grains and microcracks in the matrix improved the thermal shock resistance. And they concluded that this cyclic fatigue testing, they said it correlated pretty well with the thermal shock testing. So it's what they're saying is the cyclic fatigue testing is an alternate method of measuring thermal shock resistance as opposed to thermally shocking a sample, heating and cooling cycles. So that was a pretty long discussion. Most of these other ones are a lot shorter. So Hasselman in the 70s, he was the one that developed the thermal shock theory that we talked about with the RST and R4 parameters, and modified those parameters much later in time in the 80s. So this one is for alumina silica material, and they measure fracture toughness and spalling behavior of high alumina refractories. So they measured fracture surface energies, gamma WF and gamma MBT, for different alumina silica refractories. These are commercially available from about 45 to 99% alumina. They calculated values of RST and R4 prime And they also looked at the ratio of the fracture surface energies, gamma WF to gamma MBT. So gamma WF is for crack propagation, gamma MBT is for crack initiation. And they correlated RST, R4 prime, in this ratio to the thermal shock resistance. And they used a rapid quenching technique where they quench the samples in water. So very rapid, severe quenching conditions. So this was the delta T versus crack length plot that we looked at in the theory that developed RST and R4 prime. So delta T versus crack length, there's a minimum in these curves, the stable region and the stable region down here and the unstable region up here. To the left of the minimum, where we could have some excess crack growth due to kinetic energy, that's R4 prime. And over here to the right of the minimum, where we had just quasi-static crack growth, that was RST. And we showed these kinds of plots. This is crack length versus delta T. So in this material, we reach a critical delta T, the crack grows, and then it arrests. Then we have to go to a second critical delta T to get the crack growth in a quasi-static manner. So if we take the strength versus delta T plot for this top graph, we have a constant strength. We reach a critical delta T. We have a strength drop. This is R4 prime, E gamma over SF squared. That's R4 prime. We reach a second critical delta T before we have another strength loss, quasi-static strength loss. This is RST gamma over A squared E all to the 1/2 power. If we don't have an abrupt change in crack length or decrease in strength, we have no excess kinetic energy. We're starting at the minimum in these curves. We'll just have this kind of idea of quasi-static behavior. So we reach a critical delta C. We have a gradual increase in crack length. And on the strength versus delta TC plot, we have a gradual strength loss. And this is RST here. So R4 prime applies to materials with excess kinetic energy. RST applies to materials that exhibit this kind of quasi-static behavior. So there's a lot on this slide, but they tested, looks like 38 different alumina refractories, going from 99% alumina all the way down to 45% alumina. They measured the modulus of rupture in 3-point bending. They measured Young's modulus. This is in PSI. This is in million PSI. They measured the coefficient of thermal expansion, and this is times 10 to the minus 6 per degree C. You don't really see trends in the modulus versus alumina content or the modulus of rupture or Young's modulus because of differences in density, porosity, microcracking. But the coefficient of thermal expansion tends to decrease with the decreasing alumina content. They measured gamma WF and gamma MBT, and this is in thousands of ergs per square centimeter. They measured fracture toughness in PSI inches squared. They calculated R4 prime, that's in centimeters, and RST, degrees C, centimeters to the 1/2 power. And then for rapid quenchings at delta T's of 800 and 1,000 degrees C, you have the percent MOR retained. So the mechanical properties are measured at room temperature, and there's always a discussion since the properties change with temperature, especially the fracture surface energies, which properties do you use to calculate R4 prime or RST? One's measured at room temperature or at elevated temperatures. So these are all measured at room temperature. They measured dynamic Young's modulus. The fracture surface energies were measured by a chevron notch sample for work of fracture and a single edge notch beam for the fracture surface energy for crack initiation. Strength was measured in simple 3-point bending. Thermal shock was done on 4.5 by inch bars. And then all of these quenching temperatures were used: 200, 300, 400, 600, 800, 1,000, and 1180 degrees C. Only did one cycle. It was quenched in water, so it was severe, and the damage was monitored by 3-point bend strength. So this is this single edge notch beam for getting gamma NBT fracture energy to initiate a crack. You also get K1C from this measurement, and then the chevron notch sample gets gamma WF, is the fracture energy to propagate a crack. So this is a typical result, and this was sample number 6, a 90% alumina refractory, modulus of rupture after quenching, and then the quench temperature difference. So this is a very stable type behavior, typical stable crack propagation. This would correlate with the RST, should correlate with RST. This is modulus of rupture versus fracture toughness. So basically, the tougher the material, the higher the strength. And these are some of the aluminum materials tested from 45 to 99% alumina. There's no pattern as to increasing alumina content with any of these measurements. They just fall on what would be a pretty straight line if you did a regression analysis. Higher strength corresponds to higher toughness. And then this is percent strength retained. And this is RST. So they plotted percent strength retained versus RST. And this was at a delta T of 800 degrees C. And these are different aluminum materials from 50 to 99%. And there's a general trend here. As you increase the calculated RST value, the percent MOR increases, the percent MR retained. So higher values of RST, better thermal shock resistance. So in all these measurements, if you go back to this table, if you look at gamma WF compared to gamma NBT for any of these materials, this value for work of fracture is higher than the notch beam technique. So that gives a higher ratio of work of fracture relative to the fracture initiation energy. So this is your strength test. Sigma F equals gamma NBT E0 L0 for the initial modulus and flaw size to the 1/2 power. That was combined with the R4 prime equation, the work of fracture times the elastic modulus divided by the strength squared. And now R4 prime is shown here as a ratio of the work of fracture to the NBT fracture surface energy, and there's also a crack length in there. So I don't think the R4 prime calculations worked out very well. They didn't show it, but this ratio, which is related to R4 prime, tends to work out. So the higher the R4 prime, the higher the ratio of the work of fracture to the gamma NBT. So in terms of the microstructure in these experiments, the higher the ratio of these two surface energies, work of fracture, notch beam technique, the better the thermal shock resistance. So these materials with a high ratio tended to have coarse grains and high porosity. So they had a larger flaw size and a larger flaw density. They had lower strength. They had higher R4 prime values. But for some reason, they never made the plot of retained strength versus R4 prime. And then the unquenched samples, they did a calculation for this crack length. The cracks range from 0.078 to 0.254 centimeters. And then they calculated crack densities, 0.5 to 10 per square centimeter. So for compositional difference, the highest values of work of fracture corresponded to refractories with increasing alumina content. Thermal expansion in Young's modulus decreased with decreasing alumina content, and that's what you would expect, lower alumina contents. And the RST values increased with decreasing alumina content, probably because of the decreasing thermal expansion and decreasing Young's modulus. So as far as the test methods, the RST values for stable crack propagation correlated with the thermal shock resistance by rapid quenching, and that was by water-cooled quenching. And the R4 prime values, the resistance to catastrophic crack propagation, they're saying that correlated with the high ratio of work of fracture to gamma MBT. So basically, they're saying that any of these aluminosilica refractories with high RST values or high ratios of the work of fracture to the notch beam technique exhibited superior thermal shock resistance. So this is another early paper, and this is panel spalling weight loss and R4 prime refractory, and they're fire clay type refractory, so low alumina. So they measured properties and they calculated R, RST, and R4 prime. And these R parameter values were correlated to the results of the panel spall thermal shock test. The panel spall test, I've seen that when I was much younger, a long time ago. It's not used anymore. It used to be an ASTM test, and it's obsolete now, but it's an older test. It's quite cumbersome to run. You need a lot of samples and you need a lot of equipment. 4 samples, A, B, C, and D. These are the alumina contents from 35 to about 45% alumina. They measure the density. The thermal expansion coefficients for fire clays are pretty low. These are around 5 or 6 times 10 to the minus 6 per degree C. They measured the Young's modulus and GPA. There's quite a range here. Poisson's ratio around 0.15. This fracture strength in megapascals, and that's quite variable also. They measure the work of fracture in joules per meter squared. These are all pretty similar. Then they calculated R, R4 prime, and RST. So R is in degrees C. This is the delta T needed to start a crack growing. R4 prime is in meters, and RST is in meters squared degrees C. And then this is the percent weight loss during the thermal shock test. PS is percent spalled. So they measure thermal expansion, dynamic Young's modulus, fracture surface energy by the chevron notch bend bar, and a 3-point bend strength. Now the panel spalling test is 14 full-size straight bricks arranged in a panel. And that panel is put is actually a wall and a furnace. So you have a furnace at 1400 degrees C. You slide this panel in that wall, and then you actually have two panels. You slide them back and forth. So one is being shocked and one is being cooled. So it's cooled by forced air when it's not in front of the furnace. So you have a large panel. You slide it into a furnace at has a furnace wall at 1400 degrees C. You slide it off that wall and you shock it with a airstream. And then while you're doing that, there's another panel that slides into the furnace. And you usually do this for 12 cycles. And then you monitor the weight loss. So if some of the bricks falls off and you weigh it. It's a very simple test. It requires a lot of equipment and it's not easy to run. I've seen it run just a few times in my lifetime, and like I said, it's now an obsolete ASTM test. I don't know of anybody that runs this anymore, and I don't even know of anybody that has the equipment. So they plotted R4 prime versus this panel's falling weight loss. So R4 prime went from maybe 2 to 8, and the weight loss was from 2 to 10%. Samples A, B, C, and D. And they said, well, there's some correlation here. The higher the R4 prime value, the lower the weight loss in this test. So this was not an extensive study, but they calculated R4 prime, which is the resistance to catastrophic crack propagation. And they say it correlated pretty well with the panel spall thermal shock test results. And the weight loss decreased as R4 prime increased. So this was a pretty quick study. There was not a lot of data here, but they came up with that conclusion. And then we'll just finish up with this one. This is a thermal shock of aluminum refractories, damage resistance parameters, and the ribbon spall test. Semler and Broad are pretty well known in refractories for thermal shock testing. So this is a different type of test, a ribbon spall test. So they measured properties utilized to calculate both R, ST, and R4 prime. And then they use the ribbon test thermal shock results to correlate with RST and R4 prime. So they measured some aluminum silica materials ranging from 45 to 91%. They measured the bulk density. They measured the thermal expansion coefficients. They measured the elastic modulus, Poisson's ratio, the bending strength, and the work of fracture, gamma WF. And then they calculated R, R4 prime, and RST. The ribbon thermal shock test is utilizing 3 different sample configurations. So this is a split, a quarter, and a bar. They're all 1 inch wide. This is 4.5 inches tall. This is 2 1/4. This is 1 inch. So they shock one face of each one of these samples. That would be the hot face, and the other face is the cold face that's not shocked. So the bigger the sample, the bigger the stresses, the more thermal shock damage. So the differences in thickness produce different stress levels and different amount of thermal shock. So if you increase the sample thickness, you increase the temperature gradient, you increase the thermal stresses, and you increase the thermal shock damage. This is a cross-section of the ribbon spall test. There's a line burner here. It's a rather long burner. These are usually 4 or 5 feet long. And then there's a channel over the burner of refractory bricks. And then you lay your samples across this channel. And then you turn the burner on. You reach temperatures about 1800 degrees F. and you hold it for 30 minutes. Then you turn the burner off, but you keep the air running. So you have a forced air cooling for 30 minutes, and you do maybe 5 heating cooling cycles. So that's a ribbon spall test. And here's the length showing the burner, the 2 refractory channels, and then you lay your samples in perpendicular to the burner. So you have a hot and a cold phase. And in this experiment, they measured Young's modulus after 1, 3, and 5 heating cooling cycles. We used to run this test at Orton. We ran it quite a bit, but it's tedious and it requires some equipment. And now it is still an ASTM test, but it's an obsolete ASTM test, just like the panel spalling test. But it was a fairly good test. It just wasn't run that much. It's much simpler to take a small bar and put it in and out of a furnace. Requires less equipment. So that's the ribbon spall. So we went over a panel spalling test, a ribbon spalling test that were used in the past that are now not used anymore. I don't know of anybody that has a ribbon spall equipment set up at this time. So this is some of the results. This is the percent modulus retained versus RST. For the bars, the small bars, the intermediate size samples, the quarters, and then the thickest samples, the splits. So the circles represent different samples. So the thermal stresses are not large enough to cause damage for the small bars. So they're all up very high in retained modulus. But then the thicker samples, thermal stresses are now large enough to cause some severe damage for samples with a low value of RST. So there's kind of a knee in the curve here. So these exhibited damage, low values of RST, and then very little damage for high values of RST. And then the thicker samples showed the same trend here. Now you have thermal stresses large enough to cause some moderate damage over here, low values of RST, and higher values of RST. There's some damage, but it's not severe like in the lower values of RST. The damage is a little more here than over here. So this horizontal part, or the part that tends to be more horizontal, is a little bit lower for the thickest sample. So that was after 1 cycle, and they measured it after 3 cycles, and you see the exact same thing. A little damage here, the knee in the curve in both of these as a function of the amount or the value of RST. The damage is getting a little more severe after 3 cycles. And then after 5 cycles, you can see the curves are dropping down a little bit. So the smaller bar, again, the stresses weren't large enough to cause significant damage. As the bars got bigger, there was damage for the low values of RST. And then they did the same exact thing for R4 prime. You got the same exact behavior. The small bars, the stresses were not large enough to cause damage. And then the larger bars, you start seeing damage for low values of R4 prime. And stress is large, thermal stress is large enough to cause only moderate damage at these higher values of RST, and the more severe damage, R4 prime, and the lower values of R4 prime had the more severe damage. That was 1 cycle. They did 3 cycles. You get a little more damage, but the same exact trends. And then they did the 5th cycle, and same trends, but there's more damage. You can see the curves are shifting to the right and downward. So the R values, whether it's RST or R4 prime, seem to have a cutoff level based on sample size. So this is a 60% aluminum refractory that went through the 5 cycles, and then this is the elastic modulus retained after 1, 3, and 5 cycles. For the small bar, the intermediate size sample, and the largest or thickest sample. So you can see this is pretty constant, about 83% retained. This is lower, 35 to 45%, let's say, retained, and then the thickest sample, 11 to 37. So the thicker the bar, the more damage taking place. And for the thicker bars, the more cycles, the more damage. So they came up with this type of conclusion. This is modulus retained versus thermal shock damage parameter, whether it's R4 prime or RST. For some reason, some of these graphs didn't show up the best, but I'll get you the papers where you can read these. That'll be more clear. But they showed a trend here where there's a knee in the curve. So they're saying there's a critical value of RST and R4 prime for crack arrest to take place. Once you reach that critical, or you're lower than that critical value, you have damage taking place. So this was a flat curve for the smallest sample, the intermediate sample, and the thickest sample. So the arrows are pointing in the direction of increasing sample thickness in this direction and increasing number of cycles. So they're concluding that refractories with the higher values of RST and R4 prime incurred less thermal shock damage, and there were 2 regions of thermal shock damage separated by where that knee in the curve was, the critical values of RST and R4 prime. So moderate damage had the highest values of RST and R4 prime. Severe damage had the lowest values of RST and R4 prime. And the microstructural observations, refractories with higher values of either of these R parameters, usually the result of low values of strength and high values of work of fracture. So low strength probably means bigger cracks, higher crack density, giving rise to a higher work of fracture. And the critical values of both of these R parameters suggest that it should be possible to design microstructures without sacrificing too much strength. So this was early work. They didn't actually look at the fracture surfaces and correlate the fracture behavior. That tends to be done later in time. But they did show that either of these parameters or high values of work of fracture tend to predict the thermal shock behavior. So I'll stop there. We'll go over some newer results for luminous silica refractories next time. And then we'll follow that with basic refractories. So I'll make sure you get these papers for the next lecture. So that's what I have for today. Have a good weekend, and I'll see you next Tuesday. And again, thanks for listening.
Thank you.
Thank you.